Hi, I am Chandrasekhar Gupta and we are discussing programming concepts. Today, we'll play a puzzle. Suppose if I have 3 boxes and an object, let's take a star, and I have placed a star inside any one of this box. Now, you need to identify which box is having this particular object. One of the approach which everyone tries to follow was, they'll go to the first box, they'll open and check whether the box is having object. If it is having the object, yes, I found the object. If it is not having the object, I'll try to move to the next box and the procedure repeats. They have named this approach as linear search. There is one more approach in which searching can be done, that is binary search. Suppose if I am having 8 boxes and these boxes are having a speciality that they will answer you with yes or no for a particular question that has been posed by you. If you ask the first box whether you have the object, it will say yes, I have it, or no, I don't have the object. What do you think are the minimum number of questions with which you will be able to find whether a particular object is having in a particular box or not? Think about it. In the case of n boxes, with the help of log n questions, you will be able to get an answer. Let's see, we are having 8 boxes. I'll try to ask the first half whether you are having the object or not. The first half will say yes or no. If it says yes, I'll pick the first half and I'll ignore the second half. Now, I am having only the 4 objects. In these 4 objects, again, I will ask the first half whether you are having the object or not. Now, if it says no, I don't have the object, I'll ignore the first half. Now, I am left with only 2 of the boxes. See, now, I'll repeat the same procedure. I'll ask the first box whether you are having the object or not. If it has, it will reply with yes, or not, we'll try to ignore it. In this way, by asking only 3 questions, I have able to figure out in the case of 8 boxes. That is, we are trying to reduce the complexity by half at each and every stage. After having k iterations, the size of the input becomes n by 2 power k. And we'll stop whenever n by 2 power k is equal to 1. That is, after log n number of steps or after log n number of questions. In this case, this approach is called binary search, and this is how we will try to figure out most of the search operations in our programming language. But here, boxes are trying to answer you. In a similar way, binary search is having a condition that the array or the elements in which you are going to be searched, they need to be sorted. Why? Let's have a look. Let's try to understand linear search. Here, the element that has to be searched is 10. And let's call it as target. This is the array where we have to search for the element. We start with 0th index and we'll proceed till the last element, and we'll search at each and every element whether we were able to find the element or not. If we are not able to find, then the element is not present in the array, or if we were able to find the element in the array, then we will return its index. This exactly happens at linear search, and let's try to see how it can be implemented. If we just observe a particular task of searching or comparing an element at each and every index with the target is being repeated n times. So, as a particular task is being repeated again and again, I can use a loop over here. Let me consider a for loop. The for loop has to run n times. So, it starts with at index 0 and it has to proceed till n minus 1. I have to scan each and every index. So, I am incrementing it by 1 at every case. In every step, I am checking whether the element at that position is equal to target or not. If a of I equals to target. If I found the number, I can write yes, I found it, and I can return the index. If you observe, I is the index over here and I am trying to print the same value. If you try to look at complexities over here, we have worst case, best case and average case. On worst, if he is a pessimist, he may say that I may not find the element till I search till the last element. So, n iterations of this loop has to be repeated, and in the worst case, it can be given as order of n. If he is an optimist, he may say that I can find the element in the first index itself. In that case, the best case can be written as omega of 1. If we want to consider the average case, we can take the worst case plus best case divided by 2. Which is also equivalent to theta of n. So, if someone asks you about the complexity of linear search, it can be written as order of n. If you want to make an optimization over here, we can make it. Let's see how we can optimize linear search. Generally, here in this example, when I am trying to compare from the first till the last, suppose let's say at index 2, I found the element and this has been equal. I found the element and index has been returned. Now, after this, there is no point in searching the elements further. There is no point in repeating this task. The literal meaning is to come out of the loop and finish the job. So, if we are able to reach at this point, our job is done. And we need to come out of the loop, or else 7, 8 and 9 will be unnecessarily compared. For doing that, we have something called as break. Whenever you write break, if a program or control flow executes break, it will try to come out of the loop in which it was in. Here, it was inside this for loop and it will try to come out of this loop whenever the break statement is executed. As we have encountered break, let me give you a couple of examples where break can be used and how it can be accessed. Consider this case. Here, you are having a nested loop and you have returned break over here. So, whenever I encounter break, I'll try to come out of inside loop, but still the outside loop will be processed. The break is enclosed only inside this for loop and only this for loop will be ruled out.